All right. So hi everyone. Let's get started. So there are two headouts just like last week. Please register a time slot before today. And if you ask the question in the class, no matter in person or online, just like don't forget to email the following information to us to get the 2 points per question. So before getting started, I'll go through like 5 Q&A last time, like some of you asked about. The first is about like, will kernel be swapped? And the quick answer is no. Kernel data structure generally will not be swapped, but there are some exceptions. So for example, there are some spatial kernel related data structure like cache and like virtual file system cache, so they can be swapped out. But most of the data structure you will learn in this class, for example, the text structure, the memory management structure, file system structure, most of those kind of structure will not be swapped out. Okay. So the second one is booting and kernel code. So here's a quick answer. Actually, during the boot process, the kernel image is stored on disk, and it will be loaded into main memory by using the bootloader. So before booting, kernel image is stored on the disk. So let's say like most of the kernel source code will be compressed and then stored on your storage device. And last time we talked about the first process is called the init process in the system. And the init process will do the work to generate the rest of the process. And init process is a user process. So it is not a kernel process. Okay. And the fourth question is about if the C library is in user space, how does the operating system understand C code in kernel space? So the short answer is kernel does not use standard C library. So maybe in the next, 2 weeks, we will announce our first hands-on, and the hands-on is going to modify part of the kernel source code. And at that time, you will know like kernel is using kernel C code. So it is a little bit different from C programming. For example, when you are using the printf function to print something on your screen by using the standard C code, and in kernel, it will become the printk function. So there is a subtle difference between the kernel programming and standard C programming. Okay. So last one, I think it is also the most interesting one is kernel functions versus kernel daemon. So both are running in kernel mode because both are part of the, I would say like part of the kernel. And kernel functions is C functions compiled into the kernel image. So just like kernel module, you can load those kind of kernel module in the systems. And it runs synchronously in response to an event. For example, system call interrupt, those kind of stuff. So the key thing is they are not process or threads. So they're just like functions. So for example, we say there is system call handling, interrupt handling, or like we are going to allocate the memory from the DRAM, the memory management, process scheduling. If you are going to reschedule a process and file system, like you are going to open a file, you are going to do some the file related operations. And those are kernel functions. Okay, and I think most of the stuff in this course you will learn, most of them are belonging to kernel functions. And kernel daemon is a little bit different. Kernel daemon is a long-running kernel thread, scheduling like normal process, and it runs asynchronously in the background. So I think this is a quite difference between kernel functions and kernel daemon. Kernel functions, it runs synchronously. It means like when you are running kernel functions, you will block the systems. But for kernel daemon, it can run in the background. So it will not really block the user process. So it ensures the kernel can offload recurring or long-running tasks without blocking the user programs or other kernel functions. So the example, just like the case of the functions, just like when you open your activity monitor in the Linux, you will see there's case of this kind of stuff. And the function is to reclaim memory when free pages are low. And if you're using the joinoid file systems, you will also see there something called the JBD2. So JBD2 is going to manage journaling for the ext45 system. Okay, so those are daemons. So when you open this kind of activity monitor in the Linux, you will see those kind of like process things in the monitor. Okay. So that's it for last week. I mean, there are a lot of questions, but because some of them is quite related to the research, so I will not really respond here because we have some limited time. But if you feel like you are going to discuss those kind of research topic with me, it is also welcome after the course. So let's first do some quick recap, like what we learned last week, and it will be better for you to capture what we are going to learn this week. So we say like the computer organization, the takeaway for this slide actually is CPU is a hardware and it runs routine stuff. So what do we mean with routine stuff is when we are going to run a program, the program will be put on the, the executable code will be put on the memory. So there are several instructions here. And for the CPU, actually, it execute each instruction depends on the position of the program counter. So the program counter will guide the CPU to say which instruction we are going to execute, and CPU will batch the instruction, do the decode, and then do the execution. The thing is, the program counter only move in the predefined direction. Let's say if this is like 4 bytes stuff, then program counter always move 4 bytes, just like this, and move 4 bytes forward. So program counter will always move only forward, and then according to how much of the stride, like 4 byte or 8 byte, or like something like that. So CPU can only read out those instructions based on program counter. And maybe your question would be, then if now you are going to do some branch, if you are going to do some like function code, then the instruction will look like the jump instruction, the branching instruction. So for using the jump instruction, the instruction will modify the position of the program counter. So in this case, CPU can jump to memory address to gather instructions. Okay, but without using those branching and jumping instructions, actually program counter will only proceed in the same pattern. So we also talk about what is challenges with the operating systems. And there are 3, and it will be mapped to the process scheduler, patch for handler, and device driver. Yeah, so this is for the organization. And next week, we will also talk about what is Linux kernel. And I think this is quite important. And I will say like this is the most important like content in the whole course, because most of things after, like process scheduler, memory management, I think most of the things you can like learn from internet or somewhere. But I think Linux kernel it is a little bit subtle and it is hard to directly get from the textbook. So Linux kernel actually is a process manager, consists of a bunch of C and assembly code, and it is not a process. The reason is when we are saying a process, it should have its own virtual address space. So figure on the right-hand side as the virtual address space. So the virtual address space in the 32-bit systems, it will be the 4 GB area. So each process has their own 4 GB area, just like when you are doing the C programming, you know when you are going to allocate a memory area and you'll get the address. So that address will be the virtual address. Okay, so for this virtual address space, it will be split into 2 parts, kernel address space and the user address space. So for any process in the systems, if this is a user process, their virtual address space will be split into 2 parts, kernel address space and user address space. Okay, user address space is going to put those user program or like processing data for each process. The kernel address space is going to store the kernel functions or like the kernel data structure, those kind of stuff. So actually, the kernel address space is shared between all the user process. So you can think about, because this is the virtual address space, so it needs to be mapped to a physical address space. So all process, all user process, their kernel address space will be mapped to the same region, the same physical area, okay? So this is just a quick example. Like this is a CPU and CPU is not in the user mode. So it means CPU can only execute the data in the user address space, okay? But now if there is a cache fault, let's say if the data required by the CPU is not in the CPU cache, sorry, it's not in the main memory. So for example, if we are going to get the data from the store device, then there will be a cache fault. So CPU will switch to the kernel mode. And the mode switching between user mode and kernel mode, you can think about just like there is a register in the CPU, and the register, if the bit value of the register is like 1, then we say it is in the user mode. And if it becomes 0, then it is the kernel mode. So mode switching usually, it doesn't really consume too much of overhead for mode switching. And we will talk about the mode switching and process context switch later, like maybe I think it's next week. Okay, so when CPU trapped into the kernel mode, CPU have the privilege to execute the code or the things on the kernel address space. So in the kernel address space, there are a lot of different kernel functions, and just like there are a lot of kernel code. For example, when the CPU is going to handle the cache fault, then CPU will run the code related to the cache fault handler, and the program counter will be set to the very beginning of the cache fault handler code. So CPU can run the cache fault handler. So this is the way, like how CPU switch between the user and kernel mode for like executing the kernel related stuff. Okay, so here is a quick notice, like CPU switch to kernel mode to access OS code, but CPU does not need to switch the context. So I think this is not super clear because the thing I say context is process context. What I mean process context is it doesn't really need to switch the virtual address space. Like even now, CPU still stay at the same user process when the process code always. So this is about the like real things that it happens in the virtual address space. But I think there is a toy example here, just like assuming the submarine is a process. So process A get one submarine, and when the submarine is above the surface, then it means like CPU is not running process A in the user mode. Okay. But the thing is, if now process A needs some help from operating systems, then the submarine will dive into water. So it means CPU will switch into the kernel mode. So the thing is, actually, this is the same submarine. So it means this is the same process running on the same CPU. So it doesn't switch the CPU. It doesn't switch the process. The only difference is the state of the CPU changes. So changing the state of the CPU can run different functions in different privilege. So for example, the kernel function has higher privilege than the user function. So this is the case, okay? So quick example to go through several spatial events that will usually be triggered in the systems. So hardware interrupts, like including timer interrupts, IO interrupts, or software generated interrupt, like system call, or like errors, those kind of spatial events will trigger kernel to execute the operating system. But different event will trigger different kernel function. So timer interrupt will trigger timer interrupt handler, IO interrupt will trigger the IO interrupt handler, system call will trigger the system call function, those kind of stuff, and so on. Okay, so coming back to our toy example. So if now we have the process A now, process A is running its own program in the user mode. So if now in the program, we say it calls a system call. For example, if the program is to access like the file on the disk, for example, then it might need to run a system call. Okay, so you can think about when you are writing the program, you are going to interact with the hardware device. Then in most cases, you need the help from system call. Okay, so system call, after calling a system call, CPU will switch to a kernel mode and executing the system call handler. And after handling the system call, CPU will switch back to the user mode. So CPU can keep processing process A, okay? And after some time, CPU will, the timer inside the CPU will trigger the timer interrupt because process A may occupy the CPU for too much of time. Then in this case, we need to switch out process A for other process for fairness. Okay. So in this time, timer interrupt handler will call a scheduler to switch the user process. Okay. Because the process is switched, so we change the submarine. Now here comes another submarine called like process B. So after the scheduler finish and CPU switch back to the user mode, then the process context switch. So it switched from process A to process B, including it switched the source code from process A's program to process B's program. So now process B keep running on the user space, and then if process A needs some IO interrupt, then the same thing, CPU will switch to kernel mode to handle the IO stuff for process B. Okay. So this is the flow for how to trigger request kernel service. Okay. So those are all about the important things I think you need to learn, you need to know for understanding Linux kernel. And following on, we will proceed to the process and thread part. So process is an active program and related resource. Basically, active program, you can think about the executable file is an active program. And then related resource, including the CPU register, memory resource, file resource, networking resource, most of the stuff, they are all related resource. So you can think about like for processing register in the CPU, those kind of resource, they can be maintained in processor state. So the things called the PCB you already learned in undergraduate. Or last week we talked about in Linux, we call the PCB the text structure. So most of the register related stuff will be stored in the text structure, and most of the memory management stuff will be stored in the memory management structure, like this kind of stuff. Okay, and we say from the perspective of Linux kernel, if the kernel is going to manage all different process, a simple way will be using a list to chain the task. So there is a thing called task list. Task list is a list of process descriptor in a circular double linked list. And process descriptor or process control block, it is called a task structure in Linux. Okay, so it contains all information about a process. Okay, but task structure can link to all kind of different data structure for process. For example, if we need the file information, then there is a pointer for text structure to point to the file structure. And if we are going to manage the memory pages belonging to this process, then there is a there is a patch structures for text structure to redirect. So text structure, it is more like, you can think about it is more like a status menu for each process. But if you are going to know more detailed information, then it needs some help from different data structures there. Okay, so inside the text structure or inside the process descriptor, there are several fields. One is called process ID. So this is a unique process identification value for each process. Okay, and a quick head up, like in Linux, when we say something descriptor, it means the data structure for maintaining information for something. So file descriptor is for file, process descriptor is for process, patch descriptor is for physical patch, and so on. Okay. So, okay. We also talk about the things called kernel stack. So kernel stack, you can think about, is just like the working space for the kernel. Because when we are running the things called kernel functions, probably we need to store like the return point for the kernel functions. And we need to store some intermediate parameters that will be generated during running the kernel function. So we need some place to store this intermediate information. Just like when you are running a user process, you need some place to store your function call. You need some place to store your intermediate parameters, and you store those kind of information on the user stack. So in the kernel, same things, we need this kind of memory area to store the information. So this is called a kernel stack. Okay, so Linux kernel use this per thread memory area to store the intermediate information, including return address, kernel function calls, and those kind of parameters. And also there is a thing called metadata block. And in the implementation details, the metadata block is called the thread information. Okay, so the kernel stack will be look like this kind of stuff. So if it is a like 2 to 3 pages area. So in our Linux now we use 4 kilobyte as 1 page. So if there's a 2 page, then the kernel stack will be 8 kilobyte. It is not large, but it is important for kernel. Okay, so a thread info is stored at the bottom of the kernel stack. So it usually is stored here. And for using this information, it can redirect to the task links. So then most of the things will be stored in the kernel stack. And if the kernel is going to access the user process information, then we can use the thread information to redirect to access the task links. So this is just an implementation things for like kernel stuff. Okay. So last time I think we stopped around the process creation, but I think last time is quite hurry to finish this part. So I just redo some of the figures. I think it will be better to understand how process creation works on copy on write. So process creation, there are 2 components, the fork and executions. Fork is to create a child by copying its parents. And the reason we use fork is because it is efficient and simple. What I mean simple is because we say we have the very first process called init process. But if every time we need to create a new process and based on those kind of different settings, then probably they will fetch some error stuff if the kernel programmer or like the kernel code doesn't maintain in a proper way. So an easy way is let's just copy from the init process. So in this case, what we are going to do is to design a very good init process, including the data structure, including the process description, those kind of stuff. If we have a good design for the init process, then we can make sure the rest of the process they are set. There will not be errors there. So this is the reason why Linux choosing to fork the process. Okay. But even if forks a process, there is still some fields or like there is some status that should be different to differentiate different process, including PID, because each process has their own PID, process ID, and also the patch table, because if each process is going to have its own patch frames, then they need to have their own patch table. Okay, and some signals are different. Okay, execution is relatively easy. Execution is about loads a new executable into the address space and runs it. Okay, so it is quite easy. But the thing is, if every time we are going to copy the data from the parents, then it will take a lot of times. And in most cases, when a process is new created, it doesn't. In most of cases, it doesn't really need that much of patch frames, for example, because let's say like if the children process is born from a parent, it owns like 10 gigabyte or like 16 gigabyte patch frames. But at the very beginning for the process creation, the children process might not use those 16 gigabyte area. So here comes a technique to alleviate this kind of overhead. It's called copy on write. So copy on write is it delay and prevent copying data until the data is written. Should be sure read only at the very beginning. So like if there is a like data written, then we will do the real copy. Otherwise, like parent and children will share this resource. Okay. So here comes the example. Like if we have now process P1, process 1. And process 1 has its own patch table, and the patch table will point to those patch frames belonging to process 1. So I only draw 2 here, just like for a toy example. Okay, so the yellow part, patch frame left-hand side and right-hand side, they are all belonging to process one. Okay. So here are just a very quick analog for patching virtual address and physical address, but I'll skip it. If you are interested, you can come back to take a look. Okay, so CPU will walk through the patch table to get the location for the patch frame before CPU can access the patch frame. And the reason is current x86 CPU, it has a memory management unit to translate the virtual address to physical. So because like current like your source code, user source code now, they are all using the virtual address. So we need some translation to translate to the physical address on the DRAM. And the translation is stored in the patch table. Okay, so the first step for CPU is going to get the physical address before it is possible to get to access on the physical device. Okay, and in the patch table, I mean, there will be a lot of entries here. So inside each entry, actually, there are a lot of informations, but I don't have that much of space to draw, so I only put two important information here for this slide. The one is the translation between virtual address and physical address. And the second one is the read-write mode. I mean, this patch is in the read-only mode, or it is read-write as both acceptable. So when the stat is W now, also, sorry, actually in the patch table entry, W will be maybe like bit 0 and R will be like bit 1. But I think this will be easier to understand. So let's say just W. W means like this patch can be read and write. Okay. The privilege is read and write, both acceptable. Okay. Now here comes a request is to fork a new process from process 1. So P2 is the child for P1. So P1 is P2's parent. Okay. So when we fork the process, the thing is we need to copy the patch table, because copying patch table cannot use in the copy on write technique. The reason is if we use a copy on write technique for patch table, there will be some collision issues, like in the CPU cache, in the TOB cache, it is not easy to maintain the consistency. Okay, so an easier way is to directly copy the patch table. Okay. Okay. But the thing is, when we copy the patch table, we will change the stat for all the patch table entries from W to R. We will make the entries becomes the read only. Okay. So the entry is the entry is like when we are going to write some data to a patch, we need to first access the entry. So before the CPU can access the patch frame to get the modification on it, CPU will first know, hey, actually this patch frame is a read-only patch frame. So the CPU cannot directly modify the patch frame because this is read-only. So the write operation on the read-only patch is not permitted. So there will be a patch fault. Okay. So when there is a patch fault, then CPU know like, hey, actually, process 2 is going to write something to a patch frame. So in this case, CPU will copy the patch frame. Let us say the copy on write. Okay. And after copying out the new patch frame, CPU can write the data to the new patch frame. So if the blue patch frame belonging to P2 now, then P2 will change the BA to PA translation. Like the PA will be updated to the address for this new patch frame. Okay. And at the same time, this patch table entry, I mean the read stat will be switched to the rewrite acceptable stat. So the stat will become W. Okay. So we will only change this patch table entry. So you can imagine in the patch table there are 1,000 or even 10,000 of patch table entries. Each patch frame should be backed by one patch table entry. Okay. So because only process 2 writes the data and process 1 does not write the data. So if you look back to this yellow patch frame, actually the stat for the P1 still remains as the read-only. Okay, so this is the way for how to do the process creation, and then if there is a write operation, then how to do the copy of write. Okay, so question for this part. Okay, so if there's no, then let's move on. So this is a concept for how Linux does the copy on write, but actually Linux has an implementation for copy process, and here are several steps. First, you will allocate a new kernel stack and process descriptor. So for each user process, they has their own kernel stack. The reason is we say when we are going to run the kernel, it is based on the user process address space. Okay, so for each user address space, you can think about there should be mapped to one kernel stack. Okay, so at the beginning for the copy process, CPU will allocate a new kernel stack and a process descriptor for the new process. Okay, and after that, CPU does the copy. So copy including the copy the program counter, copy the stats, or set the PID field in the process descriptor. Okay. The reason there's two different operation is the set is you can think about because the child process and the parent process, they're using different PID. So we'll directly assign a new PID for the children. But for the copy, it is more like for safety issues, some fields will be directly heritage from their parents, for example, the stat and parent counter. So after heritage this kind of stat, they can switch their stat to some other. For example, the program counter part. So after the fork, after finishing the fork function, the fork will return to that children process to reset the program counter to 0. And then it will reset the parent's program counter to the child program counter. Okay, so this is a little bit tricky things for copy. Okay, and the stat field will be reset to the text uninterruptible. Okay, so it is initialized, it's non-interruptible. And if you are interested in what is this, you can check last week. We have talked about actually there is a stat called uninterruptible. That means like only kernel can handle this kind of stat. Okay. And after that, the parent will duplicate as patch table for the children. So the children will get its own patch table. Okay. And the rest of things, I mean, there are still. Oh, I think I can come back to talk about why copy is a decision. Maybe you think like why not just already set the field, or like why not already just set a program counter? And the reason is, for example, for program counter, maybe it is using a I'm not quite sure. Just like for example, if we use a like integer, but for stats, maybe it is using like string, and maybe for some other information, it is using floating point. So a better way to avoid this kind of errors for using wrong data type, then directly copy the data type from the parent, etc. So this is one reason why copy is a choice at this case. Okay, so for Linux, actually, I will talk about it later, but now I just want to let you know for Linux, actually, there is no process. I mean, there is no difference between process and thread. So actually in Linux, we always only call it thread. There is no process in Linux. And the reason is process and thread, the difference is how much of information they are shared between each other. What do I mean for this? Look at this. Like after duplicate a page table, for example, the open file system information, signal handlers, process address space, and namespace, those kind of stuff, if you are saying you are going to create a new process, then kernel will duplicate those kind of information for the process. But if you are going to create a thread, just like a lightweight process, then those information will share between the thread and the parent process. So actually, those information they are same format, but the difference is the information is a duplicate one or is shared between its parents. Okay, so there is not too much of difference between process and thread in this perspective. Okay, so here comes process versus thread. So thread, usually we call it the lightweight process. So the definition is it executes within the same program in a shared memory address space. Usually the thread will share the open files and page tables. Okay. So Linux implements all threads as standard process, just like they have its own tag structure. So thread and process, they all have their own tag structures. And threads have their own like program counter register, stack, and stat. Okay. But Linux doesn't provide any spatial scheduling or data structure to represent threads. So like, I mean like the scheduling between if you are using the process to create threads, actually they are in the same scheduler to do the scheduling stuff. Linux will not really differentiate. There is a thread scheduling and there is a process scheduling stuff. Okay, so the way to create thread is called clone. So the clone function is identical to fork function, except that the address space, file system resource, file descriptor, and signal handlers are shared between their parents. So you can see, like, if you call the clone functions, then you need to have some parameters, including the clone virtual memory, clone file system, clone files, and clone signal head. So those kind of things, it is going to that the kernel node, you are going to share those information with the parents. So actually, this can be customized. I mean, thread, actually, you can also say you are going to have its own file system or like has its own file. It is also possible. But I mean, basically, generally, those kind of information for thread, they are shared between their parent process. Okay. Oh, here comes the kernel thread. Actually, like I think you already know, like kernel thread is a run kernel tags in the background, and just like normal process, it can be schedulable, but it can be schedulable and it can also be preemptible. But in contrast to normal process, kernel threads do not have an address space. Okay. So let's move on to the process termination part. So termination occurs when the process or C compiler calls the exit. Okay. So after calling the exit, like there are several steps for the process to release this information or like to release this resource. So first of all, it will set the PF as X16. So PF is like process like X16 flag. So after setting up this, like kernel will know how actually this process is going to be terminated. And this like you can find in the text structure. Okay. And following on, several functions will be called like exec mm exec semaphore exec files. So for exec mm, it's going to release the virtual memory structure. So let's say address space held by this process will be released. And then the second one will be the IPC semaphore waiting queue. So those kind of semaphore stop will be the queue. And then there is also like the file related information. Actually, it is not going to release the file. It is more like the file metadata release stuff. They will be decrement for the usage count. Okay, because files can be shared between a lot of processes. So we will not directly release the file. We will modify you can think about there is a counter to share like for each process they using the same file. So we will decrease the counter or like the usage count for the file object. Okay. And after releasing those kind of information or like releasing those kind of resource, then you will call the ask notify. So it sends the signals to the text parents. And then the parents can reparent any of the text children to another thread in their thread group or the initial process. Okay. And then the last step is to call the schedule. So schedule is to switch to the other process. For example, schedule it is more like you run a scheduler and context switch. So schedule will find the next process to be executed on the CPU. So we can release the CPU resource to others. Okay, so after finishing all those kind of functions, actually the process kernel stack will be deallocated. So now the process is finally be terminated. So this is the flow for how to terminate the process. Okay, so that is process stuff. Okay, so question. Okay, if there's no question, then let's move on to the scheduling part. Okay, so before getting more information about the Linux scheduling, I think we need to first come back to do some terminology definition. So first of all, actually, there is a thing called single processor. So single processor, like you can think about like in an ancient computer, we only have one CPU and one core. So in that case, there is no truly parallelism. We call it virtual parallelism because even only one core, we can still simulate the parallelism. For example, one core can also run several processes, right? Like using the time sharing. So several processes can be served. Then this is called single processor scenario. But after that, because our CPU, even we only have one CPU, but we have multiple cores in the system. So we call it multiple processors. So multiple processors run on different, like the process can run on different processors concurrently. Okay, so this is a true parallelism scenario. Okay, and here are several criteria for schedulers. So the fairness, response time, and like throughput part. So actually, in the rest of the discussion about the Linux scheduling, we will base on those kind of criteria to talk about why Linux is going to switch from different scheduler, for example, from ON to O1 and to CFS. Okay. So I think some information for you is actually there are two very broad categories for the scheduler. The first is called cooperative scheduler. So cooperative is processed voluntarily via the CPU. Okay, but in most of the operating system now, I think most of the scheduler doesn't really follow this kind of stuff because most of the scheduler use a preemptive scheduler. So preemptive is to involuntarily suspend a running process. So it means when the process uses up the time slice, the allocated time slice, then Linux will stop the process and then switch to run other process. Okay. So assuming this is the overall process runtime. So the first triangle is about to schedule and run, and here is the preempt and run others. So the time slice between preemption and the start to run is called a time slice. So the time a process runs before it is preempted. Okay, so it prevents some process monopolizing processors. So it means like if there is no the time slice mechanism here, for example, if each process can run all the time to finish its process, then probably there are some processes they cannot really get the CPU resource. So a better way is for each process, maybe we can give it like 6 milliseconds to finish its task. But if after 6 milliseconds, the process still cannot finish its task, then we will release the CPU to other process to let the others to run first. And then maybe all the process finish, then we'll come back to design a new time slice for the rest of the non-finished process. Okay. So the key thing is, so how to decide a time slice? Because time slice, it will affect how long a process can run periodically, right? So which process should be run next is also the things that scheduler is going to deal with. So here are several considerations for designing the scheduling policy. The first is about process priority. So in Linux, we use a thing called nice value. So nice value, a larger nice value represents being nicer to others. So it means this process is a low priority process because it is going to be nicer to others. So it doesn't want to occupy too much of CPU time. So in other words, if the nice value is a smaller value, like minus something like that, then it means the process should be the high priority process because it doesn't want to be nicer to others. Okay. And there is also the real-time value. So real-time value is a real-time process have higher priority than normal process. Okay. So here comes a way to, to allocate the time slice according to the priority. Because we say time slice is quite important. If the process can get a lot of time slice, then probably it can finish its process task. But if the process get only very few time slice, then the process should be counter switch very frequently. Okay, so table on the right hand side, you can see like nice value in Linux is from -20 to 19 for normal process. I mean, in this table, it doesn't show the real-time process. So actually, if you are going to include the real-time process here, then there's, if I remember correctly, there are like 140 nice value there. So if we only focus on the normal process, -20 is the highest priority. Like it can get the time slice is like 800 milliseconds. Okay. But if your priority is super low, let's say the lowest priority and the highest nice value is 19. So this process can only get 5 milliseconds. Okay. So let's say if you get 5 milliseconds, then you need to be rescheduled every 5 milliseconds. Okay. And if you get 800 milliseconds, it means that you will be rescheduled after you finish the 800 millisecond time slice. Okay. So longer time slice means better resource utilization. The reason is, come to think about, if you can use a time slice super long, then it means like at each time for example, when the process is running, like some data will be moved from the DRAM to the CPU cache, right? So the longer the process can run, like more data can be moved from the DRAM to the CPU cache. So you can get a better CPU cache hit rate, right? But on the other hand, if the process can only get like 5 milliseconds, like the super short time slice, then maybe some of the data be put on the CPU cache and the process is going to be rescheduled. And next time the process come back to run its program, but the data is not in the CPU cache again. So it needs to be moved from the DRAM to the CPU cache to populate the CPU cache. So in this case, if you get a super long time slice, usually you can get a higher CPU cache hit. That means you can finish your task faster. Okay. But here are several challenges for this design. For this time slice, the static mapping design. Okay. So first challenge is it triggers context switch frequently if all processes are low priority. Because this is a static mapping. I mean, one thing to let you know, actually the nice value can be assigned by using the user interface. I mean, you can use a system code to change the nice value. It is possible. Okay, so it doesn't really to say like if you have 10 processes, then some of them is high priority, some of them is low priority. There's not this case. I mean, it is possible like most of the process is low priority. It is also possible most of the processes are high priority. So now if all of the processes are low priority, then the thing is each process should be switched every 5 milliseconds. But this will cause a lot of system overhead because system will frequently do the context switch to switch in, switch out the process. So we waste a lot of time to do the stuff that it doesn't really help on the process progress. Okay. So challenge 2 is time slice difference is huge for process with higher nice value. So higher nice value is called a lower priority process. So let's look at minus 19 and minus 20. So actually for process, nice value is minus 19 and minus 20. Actually, the difference is only 20 milliseconds, right? So t minus 20 equals t minus 19 plus 20. Okay, but if you look at the lowest priority process, nice value 19 and nice value 18, actually time slice 18, we can have like twice the, time slice compared with the lowest priority process. So it is quite resource unbalanced. If most of the process are low priority process, then the time slice difference is twice. But if all process is high priority process, actually the difference is super subtle because 20 milliseconds compared with 800 milliseconds, it is almost ignorable. Okay. For those two challenges, we are going to say it is not really friendly for low priority process because for challenge 1 and challenge 2, they are not really good at for low priority process. Okay, so a newer Linux schedule, I will not say this is the latest one because if I remember correctly, for Linux kernel like 5 point something or 6 point something, there is a new scheduler, but CFS, I think it is a longer, a stable scheduler they use from 2.6, I think, to at least 4.4, something like that. So we will talk about CFS, how CFS can solve this kind of problem. Okay, so let's take a hand and come back later.
I wasn't able to attend the previous week sections last week. I only signed up for this course last week. So is there anything I missed? And do I need to do anything else aside from review the previous lectures?
I think the only thing is about the paper registration. You need to register the time slot on the timetable.
Oh yes, I've already done it.
And I think no, actually, like last week is only talking about the kernel part, and you can get a slice on either.
So I just need to review the previous class.
Yeah.
Thank you, Professor.
Hmm.
之前在讲到那个hardware 的boundary，是指 OS 会越来越少 code，就是它越来越轻薄。
不是，就是这里探讨的是装置的时间的问题，就是储存装置越来越快，它越来越接近记忆体的时间。这个，那它会就是让记忆体跟储存装置的分层变得没那么明显。那分层变得不那么明显的，对 OS 影响就是 OS 通常在设计的时候是主要都是在 handle 主要storage 的问题。那以前的 storage 它可能做一个 scheduling 之类的，它可能大概就是1 millisecond 左右。那有这个设计是因为那时候储存装置很慢，所以1 millisecond 其实不是一个很长的时间。可如果当今天 storage device 一直往记忆体装置的速度逼近的话，那 OS 去做这一些决策跟判断，它其实就会影响到，就像例如，它那个数据如果是1 millisecond 的话，那到底要不要跑那个数据？对，
它会取舍说，那有些时它就不做嘛，OS 就不做。
就是会，就像是现在如果储存装置比较快的话，那其实它就没有必要每次在做 handball 的时候都做 commit switch， 对，这种感觉。
Presentation.
Yeah.
What's the policy on figures and like charts and stuff? Can we put them from the web? or do we have to be by hand? And can we also pick it from?
You mean a
directly?
bigger part?
Yeah, the figures.
Yeah, you can directly get from the paper is okay.
Paper is okay. So
Yeah, but I think I will recommend like if you are going to get a figure on the paper, I think you can do some animation to highlight which part you are going to talk about. It's like usually in the paper, the figure is quite dense. I mean, there are several information for their methodology, but maybe when you are going to introduce the methodology, you can highlight like, hey, actually this component, then you can blur the rest of the part.
Okay.
So to highlight, oh, you're thinking about this data structure, or like later you are going to talk about that data structure. Yeah, so you can do some like tricky PowerPoint stuff on the figure. Yeah.
Okay, so it's basically free for us. But
Yeah,
for
yeah.
the understanding, it might be better to. Right.
Correct. Correct. Yeah.
Thank you.
Good.
所以问一下这个我好像也不太懂。
可以，然后整个再讲一次。
好，
就是今天如果我有一个 P1 process one，然后通常 CPU 要拿就是 process one 相关的 page 的话，它要透过 page table，这样，因为 page table 是专门做虚拟到实体机体的转换。那我们现在所有的
map 嘛，
对，我们现在所有的程式都是在虚拟机体上去写的。好，那在这张 table 里面，其实它是很多很多 slot， 那每个 slot 里面它其实就会有一个对应关系，就是这个 version 就对应到那个 physical address 是怎么去对应的，这样。好，那我这边要探讨其实是，如果我今天 process one 我想要去复制，也不是复制啊，我想要去创建下一个 process， 就它的子 process 叫 process two 这样。那在 Linux 里面，我们创建方法其实就是把东西从 P1 复制到 P2 这样子。好，那有些资讯我们是可以不需要当下复制的，有些资讯是需要的，例如 page table 是需要当下复制的，所以你在 call fork 的这个当下 page table 就会被复制出来，叫做 P2 的 page table。可是 P1 所属的这些 page frame 不会被复制出来，因为 page frame 是实体的资料 ，page table 是有点像是维护资料的 metadata， 所以 page table 其实是相对来说我觉得会比较重要一点点，这样。然后它这边复制完之后呢，因为它会有个问题是，可是你今天 P1、P2 现在是共享这些 page frame 的状况，但 P2 总会有自己的 data 需要去生成之类的，所以当今天 P2 说我想要改资料，改这个 page 的资料的时候，那 P2 的这个改的指令，它其实会先透过 CPU 去查说这个 page frame 到底存在什么地方。那它这个 VA 对 PA 的转换，这应该是旧 slide， 因为新的 slide 我这边有画一个 read， 就它这边的话，它在转换的时候，它这边其实会有一个额外的 bit， 就让我们去判断说这个 table 的这个 start 它是不是 read only 还是 read write 都可以接受。因为它如果是 read only 的话，它其实不能直接做修改的，所以这时候 CPU 就会触发一个就是中断，然后让作为系统可以去做一些处理，就例如它就作为系统就帮你把这个 page frame 复制出来，然后把资料都写好，然后把这个蓝色的这个转换的关系，就是 physical address 都改好之后，然后再把它设定回去，就是 read write 都可以接受的这个 entry 这样子。那这样子的话，它就完成了一次的资料复制，然后它就可以节省很多不必要的资料复制时间，因为其实它现在只改了这个 data， 代表它只有这个 page 是新的，其他 page 其他还是可以继续保持共享的状态这样子。对，
所以它就是把那个需要改的复制过来，
对，它只会复制要改的人，
然后其他都是共
其他都是共享。对，
对，
谢谢。
我想问一下，就是如果我们就是从 P1 这边去 fork P2 之后，那一样，它这个 page frame 它借由 copy and write 去得到一个新的专门给 P2 有的这个 page frame 的话，那刚刚有说到说 P1 这时候会变成只能读取而不能再去改写，那变成说是因为 P1 这个程序已经做完了，所以它导致它被复制之后，后续只能单纯读取，不能再复改写。
没有，应该是说，今天如果换个情境 ，P1 想要修改这个 page 的话，
对，
那它就是跟 P2 做一模一样的动作。
哦，所以就变成说，
它只是想要避免，因为其实这个其实例子很简单，做2个 process，可是一般来讲 P1 可能复制可能例如10个 process 这样子，所以你不能确保说到底这个 process 现在是这个 frame 到底是被谁
是被谁用，
对，
然后他只有要改的时候，他才
对，它只要改和复制一个新的出来，
所以变成如果我回头需要修改这个 P1 的，
就一样的动作，就是他就会去 check 它这个 state，然后他知道它是 read，所以他就会把这个就是在复制出来，但是他其实会有个机制啊，就是如果他知道都没有人去 share 这个的话，他就直接改这个就好了，他就不这样子的，对，就是个小实作的机制这样。
所以他其实会把它变成他只能读，是为了防呆的概念吗？
没错，我就不能说防呆，就是因为你要有一个机制让 CPU 知道什么时候出不了 copy on write，因为 CPU 只能透过 page table entry 来去判断，就是才有这种机制可以让它 trigger OS。对，所以它其实是一个让 CPU 有机会去跑作业系统的一个手段。
了解。
对，
好，
谢谢。开个来问一个问题。
我还没有听懂，就是他的 kernel，你们这是什么意思
kernel limit 就是常驻的科农程式。常驻科农程式就像是你今天如果记忆体不够了，那你要把东西删掉的话，那它就会去跑常驻程式把东西空间清一清这样子。对，但是空间清一清这件事情跟我记忆体管理啊、排程管理跟就是system call 管理是没有关系的。对，因为这个常驻程式，它只是专门清空间而已。
哦，
对。
那你是说
它是可以跟一般 user process 同时做运作的。因为你 kernel function 是不行的 ，kernel function 的意思其实就是你今天在做事的时候 ，user project 是不能做的事，就是那个 user project 不能做的事啊。对，那它的任务不太一样，因为 kernel function 是做例如排程啊、机体管理啊这种跟资源相关的分配。对，那个常驻程式通常是做一些就是比较没有这么重要的紧急的事情啊，对，就是清一些空间出来给系统去做使用这样子。对，谢谢。All right, so I quickly read the chat box. I think there are several questions related to this process creation. I think one of the most critical one is why we are going to set the read-only flag. And also this, I think this is not that clear. Actually, what I say read-only is for the in the granularity of patch table entry. So read-only is for the entry level. So it is not really for the full page table, but because in this case, I only draw one entry, but you can imagine in a page table, there are thousands of page table entries there. And each entry, it will be set to the read-only set. Okay, so the reason to set to read-only is if there is no this kind of permission setting, actually there is no way for CPU to run the operating system. So actually this is I would say like this is a tricky part for the Linux kernel design, because if we are going to trigger the operating system, we need some like spatial events. But spatial events like system code should be triggered from the user, right? In most cases. But in this case, what we are going to do is going to realize the copy on write stuff. So this copy on write stuff actually is hidden from the user. So user doesn't really know you're doing the copy on write. Because for user perspective, user just only want to fork a process and then to write something to the process. So it doesn't really know what happens inside the what happened inside the physical address space. Okay, so a way for CPU to trigger operating systems to handle this kind of copy on write thing is using this tricky stuff, just like using this power error stuff. Because with this power error settings, if now we are going to write the data,
I think one thing to let you know, actually, for any instructions, if you are going to access the Okay, so from the perspective of CPU, each time it always needs to use as MMU. MMU is inside the CPU to translate the virtual address to physical address. So at this moment, there is a chance to check about the permission, because this entry will be directly read into the CPU, and CPU will parse this entry. You know, actually, the first part is about the translation between virtual address to physical address, and the second part is about the state of this patch table entry, or like the state of this patch. So if now the state is read-only, then you are going to write the data to the patch, then there is an error. So this error can trigger the CPU to run the operating systems. Okay, so this is the reason why at the very beginning I say actually CPU only does routine things. CPU is not really so smart, because CPU only can does the thing that are planning. What I mean planning is when CPU is going to act system, there are only few situation like hardware event, software events. And software events is hard to be generated in this kind of hardware perspective. So what we can use is the hardware event, just like we can let the patch table entries to happens the error. Then this is the way for CPU to trigger the operating system to handle this kind of copy on write stuff. Okay. So I think this is the first to answer this. And the second one, I think people are curious about like why in this scenario, like P1 should also be in the read-only. I mean, the patch table entries belonging to P1, why it should also be read-only. The reason is, this is a cool example. I mean, P1 only create P2, but in the real case, P1 is possible to create like 10 process or like 100 process here. And maybe the 100 process, they are all sharing the same patch frame. So in this case, maybe it is possible P1 is going to write the data to this patch frame. So the thing will be like P1 will send a request to CPU, say like, hey, I'm going to write this patch frame. Then P1 will run the same thing like P2 runs now. Okay, so actually this example, it doesn't really only specific for P2. This example can also be applied on P1. So for P1, if P1 is going to write the data to this patch frame, then the patch table entry now will also be updated. For example, maybe this yellow patch frame will copy to another place and then to write the new data to this like new patch frame belonging to process one. And the state will be changed from the read to write. Okay. So actually, this is a quite tricky design for like patch table. Okay. So let us for the process creation part. Okay. Sorry, I think I have one more to update for you guys. Just like maybe you have one question is if this patch frame is now only belonging to P1, because in this case, there are only two processes. So at the very beginning, P1 and P2 share patch frame, but now actually P2 write the data to this patch frame. So now we create a new blue patch frame for P2. So now this one is solidly belonging to P1 now. So now when P1 is going to write the data to this patch, actually we don't really need to do the copy on write, because inside the like patch frame, actually there is a counter to count about this patch frame is shared between how many process. And now if the patch frame say we you are the only process that using this patch frame, then the write will directly be applied on this patch frame. Okay, just like a very implementation details for this part. Okay, so that is great. Okay, so let's move back to scheduling part. Okay. So we just go through the two challenges. Like most of the two challenges, they are all related to the low priority process. And here comes the process characteristics. Because like we have process priority, we have time slice, and they are all like the criteria part, like to describe different like process resource. And there is another perspective that's process characteristics. Because as you know, like there are I/O bound process and there are compute bound process. So for I/O bound process, it means it spends most of the time submitting and waiting on I/O requests, for requests, networking requests, storage requests. So the most general example would be the graphical user interface, the GUI. So GUI is about like when you are going to interact with just like the GUI, like Windows or GUI Linux, like you are going to click some folders or like to click some like browser stuff, then actually you send a lot of like IO requests there. So GUI is IO bound because you always need to wait for the user to click the mouse, click the keyboard, those kind of stuff. And then usually the policy for handling IO bound process is it runs more frequently and interactive. So usually we will get shorter, we will assign shorter time slice, okay? Because it usually doesn't really need too much of time slice to handle because it is IO bound. So in most cases, the keyboard is, we can receive the like keyboard signal. We know the CPU can know, hey, actually you are now typing which character. So that's enough. We don't really need to do too much of computation stuff. So the thing is we need to, this IO bound process need to get more interactiveness because it doesn't want to wait too much of time to wait for the other compute bound process. So short time slice, but high interactive is those kind of IO bound process that really needs. And the process bound spends most of the time executing code. Okay, so example, the SSH keygen, just like if we are going to run some like RSS, those kind of stuff, and the MATLAB, okay, or SSH just like SHA-1, SHA-256, SHA-512, those kind of stuff. Actually, when you are going to run the SHA key, then you would take a lot of time. Okay. Also, when you are going to run something like MATLAB, then there is a compute intensive stuff. So the policy to handle this kind of process bound is because those kind of process bound process it run less frequently. So those kind of things like SSH keygen usually only runs like one time is when you are going to create a key, right? Compare with the keyboard, because keyboard is you type the each time you type the keyboard, then the keyboard should do the reactions. So it is so frequent to the CPU. But for the SSH keygen, actually, maybe in this month, there's only a few users that only need the SSH keygen service. So it runs less frequently, but usually longer time slice for them to run is better. Just as I say, longer time slice usually have a better CPU cache utilization because it is possible for the process to occupy longer time for using the CPU cache. Okay, so other than those kind of process characteristics, process priority, time slice, there are also another perspective to consider for designing the scheduling policies. It is called a maintenance overhead. So maintenance overhead, it is more like, because we are going to design a scheduler, so probably this is a algorithm plus data structures. So the overhead for the algorithm, just like what is the logarithmic computation overhead for it? Is it O1? Is it O1? Is it O log n? Those kind of stuff, it will affect how fast the scheduler can react to the request. So there are a lot of different like choice you are using a queue, you are using a tree, you are using a bitmap, all those kind of implementations stuff, okay? So, all right, let's talk about some real cases on Linux. So at the very beginning, Linux used things called ON. So ON is before kernel version 2.4, it's super old. And the design concept is, it is simple. So the background on that time is because before kernel version 2.4, as I think it's like 15 or 20 years ago, like CPU, usually there are not too much of cores, and users were not submitting a lot of jobs. So you can think about there are only very few processes need to be scheduled. So the design is all processors share a global run queue. And the thing is, how to decide which process should run first is we will sort the process by their priority in the global run queue. And the thing is, if the core is going to access the global run queue, then it needs to lock the run queue, just like when a process runs out of its time slice. Okay, so process should be inserted to an expired queue in order. So the thing is, like, there's only one global run queue. So each time, like if we are going to make any kind of modification, we need to lock the queue. So the performance is not that good. But the background is because at that time there's not that much of process, so the performance overhead is not high at that time. But the thing is, when there are more cores and the user scenario is when there are more process running on the systems, then the global run queue one day becomes a bottleneck. I mean, because if you every time you need to lock the global run queue, then the rest of the CPU cores, they will be like starvation because there's nothing to run. So there comes another scheduling is called O1. So in kernel version 2.5, the goal for O1 is performance, just like how to run the scheduler super fast, how to design the process to run super fast. Because if now you have like 100 processes in the systems, then how to design which process should run first? I mean, in this case, it considers the same things, the priority. So priority is, in Linux, there's a nice value priority. So for normal process, there are around like 40 priority. But the thing is, for each priority, there should be several processes going to this priority. So if you have 100 of process, you should go through the whole priority and then to see which process should run. So it will take a lot of time. And the thing is for O1, it maintains two very critical data structure. The first is called a bitmap, and a bitmap is 140 bits bitmap. The reason for 140-bit bitmaps is there is, if I remember correct, there are like 40 bits for the normal process and 100 bits for the real-time process. So in total, there are 140. Okay, just one more time. There are 40 bits for normal process, 100 bits for the real-time process. So in total, there are 140 bits. So 1 bit value means 1 priority value. Okay, and all right. So here for each row, there are 32 bits. So there are 4 rows here. So you can do some calculation. Now here there are 140 bits slots. So how to get the target priority value? So the thing is, because this location is the highest priority, the second highest priority, and the last is the lowest priority. So when you are going to get which process you are going to run first you are going to decide which priority value you are going to get. And then the thing is, you can directly read out this 32 bits area. And then in the Intel CPU, there is a very special instruction is it can return the leftmost bit in only bit of 1 time. So actually the reason like it designed the structure like this is because it can really fit the Intel CPU design. So why we are going to design 32 bits here is because in that CPU instructions, like it can directly read the 32 bits and then return the leftmost bit in a very short time. Okay. So after deciding, for example, because the gray part means there are the gray part means the priority, there are processes related to this priority. So like priority, I think this is like 1, 0, 1, 2, 3, 4, 5, 6. Okay, 1 and 6, they are process belonging to this priority. And the empty place means there's no process with this priority. Okay, so now we just get this priority value. And the thing is, but there might be several processes belonging to this priority value. So we need another data structure called active array. So active array, there are also 140, I would say like Q here. So Q0 means priority 0. So there's null now because there's nothing here. And then Q1 means priority 1. So Q1, there are several processes or like tasks. So task 1, task 3, they are all processes belonging to this priority. And the last one is 139. So 139, there's also process belonging to 139, and there are processes like X10, 4, and 2. So the thing is, if we can get the leftmost bit that is set, then we can directly check the which queue by using the index. So now like index 1, so you can just directly check the Q1. And inside the queue, usually we'll use the FIFO to get the next process. So the whole process, I mean the whole scheduler is super fast because this bitmap decision, it is a C2 instruction. So it should be finished in only like 1 or 2 nanoseconds. And then this data structure, I mean, after getting this bit value, the data structure can be quickly indexed by the indexing. So it should be also big O1. And this, because we are using a FIFO, so it is also another big O1. So there are 3 big O1, and then the whole algorithm, we only need big O1 to get the process, which should be scheduled next. Okay. Okay. So the thing is, after like the process is served, I mean, for example, if we pick task 1, so after task 1 use up all the time slice, then we will recalculate the priority for task 1 and impute to the expired bit array. So the thing is, the expired bit array is the same data structure with the active array. I mean, there is another 150 queues, and that is called the expired bit array. So the reason to have 2 different data structure but with the same structure is, the thing is, when all of the tasks from active array, they are moved to the expired bit array, at that time, they can switch the rule. I mean, at that time, the expired bit array will become the active bit array, and the active bit array will become the expired bit array. So it doesn't really need to have too much of the maintenance overhead. What the thing is, we just switch the like bit to say, hey, actually the active now becomes expired become active. So this scheduling, the only thing for this scheduling is the space overhead, because we need twice the this kind of array stuff. Okay, and the rest of it, performance is super good. Okay, but the thing is, the performance is super good as for the highest priority process, right? Because in this scenario, we will only pick for the leftmost bit. So here, the first we will serve for the like Q1, all the processing Q1, and the second one should be this, and the third one will be here. So you can imagine for the Q139, it should wait for a super long time for being processed. Okay, so the thing is, it is not friendly. It is not friendly for the low priority process. Super not friendly. So for the low priority process, you should get the low interactive performance. But the thing is there a way to, even it as a low priority process, it can also get the better interactiveness. So what do I mean for better interactiveness is it possible to do something like this? Like even this is a low priority process, but in a certain period, the low priority process can have some chance to run a relative shorter time for the CPU. Okay, the thing is, now you can imagine like for this, if we say for each process, you get, for example, 1 milliseconds. Okay, so for low list process here, if there are 100 process now, then the lowest priority process, you should wait for like 100 milliseconds before being running. The thing is it possible to do things like this? We we separate the time slice to like for each 10 milliseconds, we can run through all the tasks. But the thing is, highest priority can get most of the time to run, and the lowest priority only get a very slightly amount of the time. And in this way, lower priority or like lowest priority process, they can have some chance to get the CPU resource like in a better interactive. Okay, so this is the core idea of what CFS is going to do, because CFS thinks like O1 or even OM is not a really fair scheduler. So CFS is not going to improve the performance, because in the performance perspective, O1 is really good for high priority process. Okay, so CFS is how about the fairness? Okay, so the concept is instead of statically mapping time slice, each process would receive 1/n of the processor time. So 1/n is just the things I say, like if you set the time say like 10 milliseconds. So inside this 10 milliseconds, all the process can touch the CPU. The only difference is higher priority process can touch more CPU. They can use more CPU, and lower priority process can only use very few CPU resource. Okay. So the second thing is about schedule process for infinity small durations. Okay, so it is more like if we can schedule the process in a very small durations, then we can that each process have better interactiveness. Just like if every process only can only run like 0.1 milliseconds, then we can go through each process very fast. So each process can get a CPU resource. But the thing is, if we do this kind of stuff, then there are a lot of context switch overhead. So this is a balance, but for CFS, it picks for the fairness, not for the performance. Okay. So here comes an example to talk about how CFS works. So CFS relies on a concept called the virtual runtime. So virtual runtime is the real system running time plus the priority. So as I say, like virtual runtime should be look like if you are higher priority process, you still need to get more CPU resource. But even you are the lowest priority process, you don't really need to wait for all the process before you to finish. You can still have some chance to touch the CPU. Okay. So the core idea for CFS is to keep the virtual runtime of all running process the same. Okay. So here are several things to define for CFS. The first is about the allocated CPU time. So allocated CPU time is equal to schedule period times the nice wait over nice wait. So I think here are some definition. The schedule period is the period to enter the scheduler. So 6 milliseconds or 0.75 milliseconds, it depends, but it should be a constant for the kernel. So 6 milliseconds or 0.75 milliseconds means for each like 6 milliseconds, we will enter a scheduler to reschedule all this process. So all the process can have time. Sorry, all the process can share this 6 milliseconds. The only difference is which process can get longer time, which process can get fewer time. Okay, and here comes another stuff is nice wait. So nice wait is the wait for the corresponding nice value. Okay, so let's say like if your nice value is for example is 0, then the nice wait is 1024. I mean there is a table. It looks like the one moment. You will look like this stuff, just like given a nice value, you can get a time slice. But now we are not using this time slice. What we are using in CFS is a thing called wait. So the wait value is how much of the percentage you can use this schedule period. Because now the schedule period is defined at, for example, 6 milliseconds. So if you are using this table, then it's not workable. Because for this table, even the lowest time slice is 5 milliseconds. And the longest is 800 milliseconds. So it probably will weigh more than 6 milliseconds. So CFS is not using this nice value to time slice, that static mapping stuff. CFS using is dynamic mapping. Okay, so CFS is given there is a like 6 milliseconds schedule period, and for all the process, we will overall this weight together, and then we will we will allocate appropriate time slice for each process. So the formula is here. Okay, and nice K weight is overall weight of the OK running process. Okay, and later we will talk about how to design this weight value. Actually, the design for the weight value is also quite important, but later on, you can just think about the weight value. It is a little bit look like the time slice. Okay. And there is a thing called like virtual runtime, because the key thing for the CFS is to map the virtual runtime, the same across all the process. And the virtual runtime, the definition for virtual runtime is the delta execution times the nice zero weight over nice weight. Okay, so nice zero weight means the process with nice value. Okay, so we need some basis to check about if this process is higher priority or lower priority. So the basis is the nice zero weight, just like the process with nice value 0. Okay, and then this nice weight is about the definition is here, just like depends on which process you are now, then you have a nice value, then you can get away. So if now for process nice value 0, then this term will becomes 1 because nice zero weight over nice zero weight, then it will becomes 1. So you can, the virtual runtime will be equal to the delta execution time. Okay, the delta execution time is the execution time for a process, just like how long it runs. So you can image for a higher priority process, this nice weight will become larger. So this one will be the value smaller than 1. So the virtual runtime will move slower, right? Because this one, if this value is smaller than 1, then even this process from like delta execution time is 10, then if this value is only like 0.1, then the virtual runtime now is only 1. So it means like if you are a higher priority process, your time will move slowly, so you can have more time to do the executions. Okay, it sounds a little bit weird, but later on I have an example to let you know. Okay, and actually, one technical stuff for this part, actually in Linux, I say like this is theory, because in Linux it does not really look like this execution. The reason is this part will usually be a floating point number, and Linux doesn't really like the floating point stuff. So in the practical part inside Linux, the implementation is more like this kind of stuff. So actually, just like it try to minimize the floating point part by doing the computation larger than 1. Okay, so this is just a practical stuff. So let's move on to more important stuff. The example. So if we have two processes, we say process 1 and process 2, and process 2 has a like lower priority process because its nice value is 19. If you still remember, larger nice value means you are going to be nicer to other, so you will be a low priority process. So now P1 has a higher priority process than P2. Okay. So if we set the schedule period, use a scheduler, you should set the constant. So if you are using the 6 milliseconds parameter, then actually the allocated CPU time will be 6 times. If nice value 0, the weight is 1024, and nice value 19 is 15, then this will be how much P1 can really get for the execution. So P1 in this 6 millisecond total, you can get 5.9 milliseconds to do the execution. But P2, you can only get 0.1. The reason is P2 is a lower priority process. So in this 6 milliseconds, it allocates most of the time for higher priority process, let's say P1. But in this 6 milliseconds, P2 still has 0.1 millisecond to get a chance to use the CPU to do some processing. So if P2 is an interactive process, then this is a good combination, because P2 usually doesn't really need too much of time. But the thing is, if we are using the traditional scheduler, for example, O1 or ON, then P1 is nice value 0. So let's check the table. So here, nice value 0. So P1, you can get 100 milliseconds to do the execution. And P2 can only use a 5 millisecond. So the thing is, P1 now can first run for 100 milliseconds. Then P2 can run. But P2 should wait for 100 milliseconds. And if we are using the CFS, then P2 can run after every 5.9 milliseconds. So P2 can get a better interactiveness. Okay, so here comes a more like true example. So initial virtual runtime for each process, if we set to 0, and P1 is a higher priority process, so let's run P1 first. So P1 run first, and the thing is, actually, until now, we do not talk about one thing as I/O. I mean, we only talk about there's a thing called time slice, right? But actually, in a real system, there are I/O. So I/O comes here. So when P1 is running, and if it fast I/O after 1 millisecond, so the thing is P1 can run for 5.9 milliseconds, but because there's an I/O, so P1 should stop here because P1 should wait for the I/O finish. So P1 will do the context switch to P2. I mean, P1 should release its CPU to other process, and now the process is called P2. So P2 takes over, and after 0.05 milliseconds, I mean P1 finish. So in this case, P2 should be interrupted, should be preempted, and then P1 can come to take over P2. Okay, so let's do some calculation. So because after 0.05 minutes, P2 should be stopped because P1's data is ready. So here comes the decision is P1 and P2 who should run next. So if we calculate the virtual runtime, P1's virtual runtime will be, because it run for 1 millisecond, and wait for P1 because it has nice value 0, so it is 1 now. So P1's time, virtual runtime is 1. But the P2 only run for 0.05 milliseconds. But when we look at this part, because this part, the calculation will be nice 0 wait. So it's nice 0 wait is 1024. And for nice value 19, the wait should be 15. I mean, there is a calculation later, but we say assume now nice value 19 is 15. So this part after the calculation will be 3. So actually P2 run more virtual runtime than P1. So P1 should run next. So P2 will be stopped and P1 can keep running on as like process progress. So this is how CFS run, and P1 will preempt P2. Okay, so how to maintain this data structure? I mean, we now only have 2 processes, so it is quite simple. Like, you know, P1's virtual runtime is more than P2, so you pick P1. But in Linux now, you have 100 or even 1,000 of processes now. So Linux decided to use a thing called red black tree. So the reason to use red black tree, there are 2. The one is it is a balanced tree. So because it is a balanced tree, so there is usually no skew branch. So if there is no skew branch, it means it has better predictiveness. Predictiveness means if now you are going to get the data from this tree, then at most you only need to touch 3 levels. So you can predict how long you can get the answer. And this is super important for Linux, actually. And the second one is because you are using a red black tree, so including the insert, search, and delete, the time can be measured. If I remember correctly, it's like, is it like log n, something like that? Okay. So this is the reason why red black tree are using in this CFS scenario. And the key thing for red black tree is the virtual runtime is the root for each node, is the index value for each node. So 5, 30, 50, 80, 70, 90, they are all virtual runtime. And what CFS will really get from the red black tree is the leftmost node, because leftmost node means it has the smallest virtual runtime. Okay, so in this case, you can think about P1's virtual runtime is 1 and P2 is 3. So P1 might be here and P3 might be somewhere here. So P1 will be get directly from the CFS. So the reason we say we are going to get a smaller virtual runtime is smaller virtual runtime implies the most need of CPU. And larger virtual runtime means the least need of CPU. Okay, so smaller virtual runtime here, P1 will be peak and P1 will preempt P2. So this is how CFS works like. Okay, so question? All right.
Can I just clarify? In adding the V runtime, how do you get 1024 over 1024 and then 1024 over 15?
Okay, I will answer this in the next slide. Actually, it depends on the calculation. So the next big question is, so how to decide the weight? Because the weight is quite important for us to decide the true virtual runtime. Okay, so actually, the decision behind the weight is it follows a thing called a 10% effect. So what do I mean 10% effect? Okay, if we look back to this scenario, so if you now let's say time slice is weight. Okay, so if you look at like nice value 18 and nice value 19, actually the time slice 5 milliseconds and 10 milliseconds, the difference is 2 times, right? Because 10 divided 5 is 2 times. Okay, so 10% means we are going to let every nearest nice value difference to be within 10% difference. And it should be controlled the 10%. So actually in Linux, if you open up the Linux kernel, I think any version after 2.6, you can get this kind of field. And like this field will let you know like, oh, actually, nice value 19, you can get a weight value 15. And if you are going to get the highest priority process, the nice value minus 20, you can get the add 761. So it will be super large. Okay. So the key things or the important critical things behind here is if you do some calculation, you can find the difference between between two weights, the difference will be around 10%. So I mean, there is a mathematical proving for this part, but I'm not going to prove this thing. I mean, if you are interested, you can go to check the ChatGPT or the Linux Foundation. They will tell you how to do the proving about actually there is a formula that can generate this kind of weight, and each two like weight, the difference will be around 10%. Okay. The reason now like it is fair for low priority process, because like even for low priority process or highest priority process, the difference they are all around 10%. Okay. Okay. So this one is about how to calculate this kind of weight. So like actually it is about 1024 times 1.25 over the like nice value. So I mean, while it is 1.25, I mean there is a calculation behind it. I mean after some method proven, they will tell you actually if you are going to get the 10% effect, then you should be follow this kind of formula. Okay, so that is how to decide the weight value. But I mean the core idea is how to make the weight value between any two weights to be within 10%. Okay, I think this is the core. And I mean in the exam, I mean there will be no question about how to do this kind of calculation. Okay, so don't worry about. Okay, so that is about the CFS part. Okay, question. All right, so if there's a question, then let's move on. So we talked a lot about the normal process, but there is also a category inside Linux. It's called real-time process. But I will not talk too much about the real-time scheduling thing, because actually there is a course called real-time scheduling. So if you're interested, you can get that course. But I can give you some very brief idea about what's the difference between the real-time and normal process. So there are two different categories of the real-time process. One is called the soft real-time, another is called the hard real-time. So soft real-time is kernel tries to schedule applications within timing deadlines. So Linux only provides soft real-times. So the counterpart for this is called hard real-time. So systems are guaranteed to meet any scheduling requirements within certain limits. So soft real-time just means like you can break the time limits, but not too much. Just like maybe there is a couple of milliseconds, it is acceptable. But hard real time is you should finish the process in some like criteria, for example, 1 millisecond, 2 milliseconds. So the use case for hard real time, it is more like in the automatic driving systems or the Air Force pilot systems. So those kind of systems, because they are using the auto driving. So when there is some accident happens, they need to control the operating system can react like within like maybe 1 millisecond or like several nanoseconds. So then this kind of hard real time guarantee. But for most of the case, I mean, because Linux is used for the, I would say like general purpose operating system, so it only follows the soft real time. Okay. So Linux real-time scheduling policies, like including 0 to 99, they're all real-time process, and there's the rest of it from 100 to 139 is normal process. So this is the reason why in O1 we have the bitmap as 140. Okay. And in the real-time scheduling, actually there are several, and I think you already learned in the undergraduate, because in the undergraduate, what most of the scheduler we learn is designed for the real-time. So including the FIFO. So FIFO, if you open the Linux source code, there is a scheduling policy called schedule-FIFO. So if you choose this one, you are using the real-time scheduling. So tasks continue to run until it blocks or explicitly yields the processor's code. So this is FIFO. So FIFO tasks have no time slice and can run indefinitely. So that means like FIFO just you start to run this process, and the time for next process is the prior process finish. So it has a super high priority. You will not be interrupted in most cases. So only a high priority FIFO or the round robin task can preempt. I mean, just like the real-time process can interrupt the real-time process, but normal process cannot interrupt the real-time process. Okay. So there is another thing called it is going to let the real-time process have some chance. I mean, the lower priority real-time process has some chance to use a CPU. Okay. So process context switch. Okay. So process context switch. Let me do some quick definitions on the process context switch part. Okay. Because I think this topic is quite important. Like this is related to, for example, if there is a patch fault, if the data is in the storage device, then you learn like maybe we should run the process context switch. Or if there is a process use up all the time slice, then the scheduler will call the process context switch. So the key thing here is we are going to switch two process. But before doing this kind of stuff, we need to do some definition. So what is a process context? So I think basically you can think about process context is just like a workspace or playground for the process to do the execution. So like most of the resource related to run this process is called process context. So it includes user address space, just like patch table, this kind of stuff, hardware register. I mean, not only program counter, there are all a lot of register, they are all related to process context, and kernel data structures that relate to the I mean, the only things doesn't really include for process context, I think, is the source code part. So the rest of the CPU, memory, and those kind of storage resources, they are all belonging to the process context. So I think this is a broader way to say, actually, this is a workspace for this process to run. Okay, so you can also think like context is very similar to an environment to run something. Okay, because actually in this course, we will talk about process context, but in Linux, it doesn't really only have process context. I mean, if you go to a Linux source code, you can see like there is an interrupt context, those kind of stuff. So interrupt can also has their own context. Okay, but we will not discuss that in this class. Okay, so process context switch is switching from one runnable process to another. So there are two key steps for the process context switch. The first is called a switch MM. The other is called switch to function. So the switch mm function is to switch the virtual memory mapping, so including the patch table and TOB, because we are going to switch to another process. So for that process, it needs the help for their own patch table to access the patch frame. Okay, so patch table, and because patch table entries usually can be cached in the CPU, and the device is called TOB. So TOB is the hardware to cache the patch table entry. So the second one is switch to function. So switch to function is to switch the process state. So to switch from one to another. Okay. Okay. So I think let's call it a day and see you guys next week. Yep. Thank you.
为什么这个要选15%而不选15%或50%？
其实这个可以选择15%或15%都可以，但是它就会改动到这个位置。当初选10%只是一个经验法则，就是说10%是一个差不多的值这样子。但是你要5%、15%、20%，其实都可以证明出来，它其实是可以做挑战的。哦，对，所以它没有一定是10%，只是 Linux 现在是用10%。对。
所以这边它跟原本做法差异是，原本的那个 nice value 对应到一个 time slice，那现在它 nice value 又对应到 time nice weight，然后再对应一个 time slice，对，它多一个 time weight，
就是原本的 time slice 是固定的，查表就可以得到 CFS 上算，因为你不知道，因为它是看 weight 的对应，而且它的 weight 对应不是直接对应，因为它还会除上它的基准的那个 nicely 那个人的 weight，所以它需要去算它现在的 time slice 剩多少，这样。对，就你可以想成 CFS 是动态去算现在的这个 virtual runtime 跟 time slice 多少，然后那个传统的做法是固定的，反正你什么 priority 你就得到多少的 time slice 这样子。
那这边的公式可以解释一下 lead runtime。lead
runtime 的公式其实就比较像是说，你说公式本身吗？还是公式本身就是 delta S 就是这里的定义，就是它就是这个 process 现在跑了多久，实际上跑了几秒，或者是几微秒这样子。然后呢，它会做个转换，因为它后面这个 nice value 除以 nice k， 不好意思，下面这个 nice 零位除以 nice weight， 就是想让它的这个时间对应到虚拟的时间上面。为什么要对应到虚拟的时间？因为如果你直接看这个时间，看这个例子，这个时间来讲的话，其实它 P2 只跑0.05秒而已，对吧？照理说它跑很短，对吧？那 P2 应该可以继续做，可是因为 P2 的 priority 很低，所以它需要有一个对应低 priority 的真实 CFS 看到它跑的时间，所以它在这边做了一个转换。就 P2 算完之后，其实它已经跑了，对于 CFS 来讲，它已经跑了3秒，你可以这样想。那这个例子来讲的话，它就应该跑 P1， 不应该跑 P2， 因为 P1 的优先权高，所以 P1 对于 CFS 来讲，它可以分到比较多的时间段。所以 CFS 看的不是它真的跑多少时间，是看它转换完它的虚拟时间跑了多少，这样，所以才会需要有这一层转换关系。
这个 delta execute 是什么？
就是它现在跑多久啊？实际上它现在跑多久？就是这里 execution time for a process。对，就是你在现实世界这个 process 现在距离你上次被执行到现在跑多久这样子？就你被唤醒之后到现在跑多久时间？
那这样的话不会，就是他用的做法就是骗 CPU 说这个其实会花的久，然后这个花比较少。
你也可以这样理解，对，所以它叫虚拟，它叫 virtual。对，但其实对于 CPU 来讲，CPU 是管这些事情的，因为 CPU 只会做你写的 code 是怎么写的，它跑什么东西，所以你也可以想这些东西都是 CPU 自己在算，自己在跑。对，所以 CPU 也没有被骗，只是 CPU 知道说你就是用 virtual runtime 去做排程。
哦，他就是用 virtual runtime 做排程。
对。
那原本来说 P1 是，就是在原本的机制，我们都只会做 P1。
对，我们会等 P1 的时间都用完，那再来换 P2。
哦，那现在我们多做 P2，但 P2 又会被拦截掉。
对。
好，那我先看下一个。
我想问，你可以再跟我解释一次，它这个时间是怎么决定要长还是短？
这个时间比较特殊，就是基本上它只会有两个6或者是0.75。那它的决定的方法其实是，就是 Linux 有建议说，如果你的是 process 总共超过8个的话，你就用它6比较好。就经验保证，你用6会比较好一点，因为不然的话，你那边切换的成本会很高。但如果你 process 很少，就0.75就可以了。
那它是怎么定出6跟0.75这两个词？
这个我没有很确定，但是我的理解是，它会透过去计算抗内数据所需要多少时间，然后你排成的这些成本是多少，然后它就会有一个经验法则告诉你说色难。但你也可以自己去改它，然后就什么10 microsecond 啊，10 millisecond，
他们测出一个比较好的值，这样。
对，就是它也是跟你跑多少 process，然后理论上你跑多少 process 会有关系。
对。好，我想理一下，所以这个 fork 它的那个复制是包含它这个就是老师刚刚讲到的这个 page table 转换也都算它 fork 的部分，所以我还是一个完整的 fork。
对，就是你也可以想 page table 其实就是 process 的一个部分，然后 fork 就是把整块都复制出来。
对，可是复制是也包含说它创造一个什么，比如说创造一个新的 page frame， 算是 fork 的整个完整的过程，就这样子。
不算，
还是
创造新的 page frame 是 fork 完之后你开始运行了，然后这个 process 想要去改某些东西，
所以它是到 SQL 的部分才会被创造这个。
对，因为 page frame 才是真正贵的，就是你 page table 顶多让你有一个1、2 G 已经超大了，可你 page frame 你动不动可能就是什么10 G、100 G 这种，所以不太可能把 page frame 直接就复制一整份出来。
所以 fork 这真的就只是复制这边而已，然后到了 SQL 的部分才会去动到，不会创造一个新的 page frame。
对 ，copy on write 是 SQL 它才会有。
好，谢谢。
我问一下，这 kernel stack 有没有几率是会被塞爆的？
有。
对，那塞爆会是怎么样？
塞爆要怎么解决哦？就是塞爆的话，它其实会去做一些回收的动作这样子，但是或者是资料压缩，但是塞爆的情境很少，因为塞爆的状况是之前是32KB 系统比较容易塞爆，但你现在你们系统都机体都很大，所以其实它基本上是不会塞爆的。对，但是塞爆它就是去压缩这个资料，然后反正就资料可以做一些压缩，有没有？然后避免它爆掉。对。对，
所以这个 task track 主要会去指到这边 kernel stack
对，他们是可以互指的，那大家可以去透过去走访这个资料结构，你就知道说你的 kernel stack 在什么地方。因为 kernel stack 是每个 project 都会自己的 kernel stack， 就是让它自己在变成 kernel mode 的时候可以执行的。对，
原因这样做是因为这个通常是很大的。
没有，应该这样说，就是这个结构它会这样做，是因为假设你今天要去做排程，好了，会在 OS 里面做排程，但你想知道所有人的这个排程的演算法是用什么，所以你就需要这个资料就会快速去知道说其他人排程都会用什么东西。对，所以它其实只是一个比较快的，就是它这边说的就是 metadata， 比较快的可以去找到这些资讯的地方。对，是啊，对。
我想问一下，就是这边有讲到它是一次是做32 bits，
对，
这个跟就是我们平常用Windows 32 bits 是有关系的，
是有关系的，就是32位元跟64位元是因为 CPU 是32 bit 或64 bit 的 CPU，对，所以它会因为位元的不同，然后就会出现一些相容性的问题。对，那这个32 bit 是因为这个假设是它是用32 bit 的x86 CPU 去做的。对，那我记得如果它是64 bit 的话，它就是可以一次吃64 bit。
就是这边就是2倍的。
对。
这个，可是当初就是用 arbitrary 存，是因为就是从顺序小到大是存它的那个 virtual。它每次执行过后，就每次 switch 进去之后，它这个
都要换，
每次就要再重新建一个。
有，因为 arbitrary 优点就是因为它的更新很快，所以他选择 arbitrary， 所以他每次就要去做这个 arbitrary 的更新，就是更新这些 virtual runtime 到正确的资讯。对，所以这还是为什么他选 arbitrary， 为什么不选别的 binary search 这种的？对。
刚刚讲到就是用 arbitrary 的另外一边，是因为它是可能 balance， 所以它的高度不会太高。
对。
然后我没有很理解，就是高度是高度。
高度如果差异很大，就是假设它有一个 skew 的状况，它会走很远的话。Linux 会没办法控制说，因为你很有可能会跑到这个很远去，但也有可能是在很短的，所以 Linux 没办法确保你这个 instruction 到底要多久才回来，因为它要去走访这个 tree。那它有时候就因为毕竟 Big O 这个东西，它只是说平均概念上它可能是多少，可是它实际上你可能你要走这个很深的，你可能会走一个比较久的时间。 那 Linux 就不知道到底是你走了很久，还是它出现错误了，所以它无法回来这样子。所以一个平衡数来讲的话，它的好处就是 Linux 可以很好预测说，我举例来说好了，它如果超过可能10 microsecond，不好意思，10 millisecond，Linux 就会觉得它出错，它就会把它砍掉重练这样子。但是现在如果这个 tree 是歪斜状况，它很有可能这个分支就会超过10 millisecond，那 Linux 就会判断错误，然后它就会砍错，对，就这样。谢谢。
关于那个 copy online 的问题，就是你在 fork 之后，等于是2块 page table 都会变成 read only。
对。
我是只要遇到 read only， 我就知道说它是 copy online， 应该不是。它是就是 kernel
哦，真的，这个好问，好问。
说它是什么？
应该，我觉得你应该这样看，就是它是 read only 的 permission， 但你现在要 write， 所以 kernel 就会去，对，不是 kernel，CPU 就在这时间点触发 page fault， 然后 page fault 其实有很多可能性，然后这个就检查说到底是什么造成它的问题，对，
他就是查那个，
他就会查错误的，对，错误的讯息这样子，对，但通常这种状况其实就是 copy on write， 对，因为就这2个嘛，就 copy on write， 不然就是它就是不能改。
对，他不会说，
它就是不能改，
块是，
对，它就是唯独的，对，那也是有可能，但是他就会去查 page fault， 因为 page fault handle 其实是一个蛮复杂的结构，就是它会去查各种可能性，就看你是什么原因造成的。那一排除之后，他就会知道说，哦，这是 copy on write 这样。对，他这样，好，谢谢。问啊。
报告的话是可以用中文讲，还是要？
可以，不用，用你熟悉的语言讲就好了。
好，就是之前就是因为我是大学是机械系，
然
后我以前就是就有学过，怎么说计算机还有那个资料结构都有去过，你会觉得说这样修这门课，我修这门课会很吃力。问一下，你会觉得这门课，因为我看你写不到跟 beginning， 但是
我觉得应该还好啊，因为其实资料结构我们用的其实不这么多。
你说哪一个？
资料结构用的其实没那么多。
那计算机组织，
计算机组织应该只有在最一开始的时候会，就有那些而已。对，后面都是比较偏就作为系统的一个设计。
是因为我觉得相对来说更喜欢跟真
的啊，
其
实蛮正常的，因为但是我觉得你可以这样想，大部分的职工学生应该不会觉得听得很简单，因为毕竟原本的大学部 OS 没有教到这些比较，它其实不是比较难，它重点是它是比较偏实作，所以它就比较 specific 在某一些实作细节里面这样子。
然后可能用纯英文的时候，可能大家比较不是大家平常熟悉的语言，
对，
所以
没错就会比较卡。但是我觉得就多看几次投影片，其实我觉得就应该就可以。
然后你
因为往年的
录影再这样，
是的，因为往年的分数其他都蛮高的。
真的吗？
对，往年应该 A 加应该一半以上吧，或者是可能更多。
那老师，那我问一下，考试大概会怎么样去考？比方说考 PPT 吗？还是考
就是差不多
作业
PPT 跟东西而已。
作业
就是因为它是
观念嘛，
对，观念题或者是名词解释，
但是也是要全英文，就是所以要很熟这些英文。
对。
OK，那所以老师这2个小时就是刚上个也是全程录的。
对。
好，OK，那作业是都会用 C 还是用 Python？
都会用 C。对，好，因为作业都是改 kernel， 所以都只有 C 可以改。对，但它的 C 不是一般的 C， 它的 C 是 kernel 的 C， 所以会大家熟悉一下。反正你们写都知道了，反正你们很多方面是不能用的。
好，对 ，kernel 是，那这样我的电脑还要就是换成那个，就是用 Windows 应该也是可以吧？
可以，我们会跟大家说可以用虚拟机器开，因为我们这次会用 RISC-V 的 CPU， 所以大部分人应该都不能碰，大部分人都要用虚拟机器。
虚拟机是 Anaconda，
是那个 VMware 那种的 VirtualBox 啊，这种的。
VirtualBox， 好，我回去再查一下，因为我好像从来没用过。好，
OK，可以，我们应该会有个 guideline 啦，我记得助教他们会有个 guideline。
对 ，OK， 对。所以真的是 welcome beginners， 应该是真的 OK 了，
真的 OK 了。
好，
因为往年大家都系都用很高分，而且往年都不是自动系，就是自动大概只有一半的人，然后其他还有很多别的系统。对，
其实看这门课开到330，应该都是蛮多外系，像
就我觉得不会到很硬。对。
好，现在是机械系，然后现在是电控所，对，好 ，OK，
可以的
，OK， 可以，好，谢谢老师，
可以，谢谢。
然后我不太懂，就是他这里为什么是O1？
因为他做所有动作都只需要O1而已。
可是他不是每次都要从这里开，
但是这个是个 CPU 的有效性可以完成，所以它有个 CPU 的特化是 我直接把32bit直接读进去，它会在O1的时间直接跟我们说是哪一个 bit 是有值的。对，就是它是这个硬题解，它这个是硬题读进去之后，硬题就直接告诉你哪里会有第一个最左边第一个在哪里，它就会回传一个 index， 就说哦0它这个状况是1啦。
然后所以我们把它假设成就是它是一个指令，
对，它是这个指令而已。
那它这个就是它没有，它这个不是一样，你都要就是它也是一个 Q， 然后你要慢慢一个一个找，那这个不是吧？
不会啊，因为你这边你知道这是 index 多少，你就直接这边139Q 直接拿 index 就找，所以这也是一瞬间而已。因为它就是看 index，所以这个1就对应到1，6就对应到6，所以它都是 O1 就可以结束了。就是你 index 多少，就有点像是你有 array 直接给 index，它就直接给你回传这一串。然后这里面有很多，但是它用 FIFO， 所以都只会找第一个而已，所以它每一步都是 O1 就可以做到的事情。
哦，
对啊。
哦，
对，所以它是有稍微设计过的一个状况。
哦，
对。等一下哦。
对的，是啊，还有哪里？原来总点也是蛮好。
哦，我是我，
因为子弹总点是那么大。
来，
罗老师，确认一下，O1 和 O1 的差别在于，像 O1 的这边的 就是它选取第一个也很快，
它第一个也很快，但是它不会只选第一个，因为它对于整个 global queue 里面的 process 做排程，不好意思，做受控，所以它需要 N 的时间。
哦，它先排程，然后再选第一个。
它先那个
排序
再选第一个，
所以它不是一个 priority queue 的吗？
它那时候并没有 priority queue， 对。但是要 priority queue 也是可以，但它还是 O1 啊，因为它的整个维护时间就是接近 N 的时间，对。
哦，
因为它这个里面的这个 priority 是有可能会更新的。
哦，
对，所以它是会一直，而且它有可能会有人新增进去，所以它总共来讲，它也是会归纳成 O1 这样。
那这个不管是选取第一个或是 insert 都很快，因为插入的话只要变140，然后插进去。
对，没错，它插入也很快，而且它只需要把那个 flag 设成1，所以它其实整体的速度很快。
哦，
所以他们能那么快，就是因为就是高手那个也刷新。
对，它能那么，它其实最慢的应该是这个查询，但因为它那个引刷线把它加速，所以它才可以是 O1。因为其他的都是设计过，所以其他本来就是 O1 可以做的。但是只有这一步本来其实是要做 L9的。
真的吗？
对啊，因为本来这步要直接扫过去，你更不知道哪里是左边。
就不能先记录哪个是第一个，然后下次直接选取它。
可这样你就要有一个记录的成本。
他会改。
对啊，
然后改。
而且记录的那个 parameter 变成是要有那个维护，就你可能需要有一个 sample version 来做维护，你不能让它同时改。但这个资料结构呢，是就是作用在多核心的状况，所以它是资源你可以多个 process 一起去用的。
所以那个 instruction 其实上课没有讲，但它其实有点特别，它只是设计的 OI。
对，但你也不能说它特别，其实就是 CPU 有提供那个方选，然后它的做 Linux 的时候，它就把这个方选拿来用这样子。对，它把这个 instruction 拿来做这个设计。对，所以它可能是一个 general 的 instruction，只是它刚好 Linux 知道有这个地方，然后就把它拿来做设计。其实 Linux 有很多设计都是基于 CPU 提供很多功能，或者你也可以这样想，就是 Intel CPU 在做设计的时候会跟它改过的 kernel code 去做结合，所以去做硬体的加速。对，所以这也是为什么一开始要跟大家说硬体结构，因为其实是要暗示大家说 Linux 有很多设计都是绑定 Intel 的 CPU 的。对，就是这样才会快。那当然，你说别的 CPU 可以吗？一定也可以，只是它相对来讲做的事情就会不太一样，有些时候它就不会那么快。对，大概这样子。
那这边的话，刚刚老师你提到 Jira execution，是实际执行时间。
对，是实际执行。
那它是 allocated CPU time 吗？
不是 allocated CPU time 比较像是我今天要每次的重排序，我需要多久去做重排序？应该这样讲，就是 allocated CPU time 比较像是你今天有10个 process，我就给你总共一个 allocated CPU time 去跑完这 10个 process，每个人都要跑过一次这样子。对，有点像是去决定多久要重新整个重排一次，整个 reschedule 一次。对，就是我如果给你6 millisecond 好了，代表我这10个 process 在6 millisecond 一定都可以碰到 CPU 一次，这样，这是 allocate CPU time 的意思。就是他想要限制，他希望所有的 process 都可以在一个很短的时间都可以被排程到。对，那跟之前不一样，之前这个地方 allocate CPU time 你可以想象成就是，每个 process 都会很长，因为它的那个高 priority 都是什么几百 millisecond 这样子的。对，所以你光等到你也可以执行的时候，你已经过了不知道几百 millisecond。但你这个是无论你有多少个程式，所有程式都可以在这个 allocate CPU time 规定的时间去碰到一次 CPU。对，就你一定可以只到执行到一次，因为根据这个 virtual runtime， 假设你今天 priority 真的是超低。但你超低再怎么样，你是在原本的这个后面，你总有一天会到前面来。那你高优先权的人，你会随着你用的时间越多，你就会越来越接近你这个用完的时间，你就会被排到最后面去。对，比较像这样。
所以它就是allocate CPU，它是先规定一个大的时间间隔，然后每个这个时间间隔一定要做完10个。
对，
然后之后
就是高
会实际执行
对
delta execution time，然后 delta execution time，CPU 怎么看它，就是把它放大成
没错
virtual runtime，然后去看它。
对，没错。
那所以这个东西它不是 per process，那后面这边的计算是，因为这个东西它是所有 process 的那个 nice weight 加起来嘛，就是这个 nice k weight。
不好意思，我再讲一下，我就刚才有地方讲错，就是这里的 allocate CPU 他们是给定那个时间里面每个 process 可以拿到最多多少时间。
给定时，
就是它有点像是刚刚讲的那个 time slice 那种感觉，但是它是用算的，就是 allocate CPU time，假设我们这个 schedule period 其实是个定值，它每次大概是
你刚刚说的那个给一个 window，然后比如说10个 process 每个都可以摸到一次，那个时间实际上是 schedule period。
那个时间其实是那个，就是那一段时间就是 schedule period，对我 millisecond 就是 schedule period，对，然后至于每个 process 最多可以用多少时间，那就是 allocate CPU time。对，它就是根据这个 weight 去做计算，就是越高优先权呢，你就是可以拿到越多的比例，这样子。就是 CEBS 它其实就是讲出了一个比例，高优先权它就是拿到比较多比例，低优先权就拿到比较少比例。对，那它这个比例之外呢，还要再加入一个虚拟的这个时间。对，因为虚拟时间的好处就是它可以去像这样的，就是虚拟时间放大之后，你还是会很长这样。对，然后高优先的人就有比较多的机会去碰到 CPU，因为毕竟虽然我们说我们要让低优先权有比较好的互动性，但是对于高优先人来讲，它也需要有好的互动性。所以它这个设计会说让某种程度就是在确保高低优先权人都有互动性，但是高优先的互动性更好一点，这种感觉。
OK，
好，谢谢。
就是刚刚上课的一个小问题，就是像这种in class 的话是上课的时候问，还是说下课问？是这种 in class 的？
就是在这堂课我离开之前问都可以。
好。但是如果说就是像这种就是现场的话，那第五个这样要怎么办？
现场这样你就直接说是问哪个问题就好。
OK。
对。
然后这个是助教的信箱。
对，没错。
所以如果考试的话，就是如果考试的话就是以那个投影片的观念为主。对。然后最好是就是因为像我也是数学的小白的话，就是应该是每个投影片最好都要很熟悉，大概就是在讲什么。
对，但其实考试会考得难，所以我觉得是还好。
你说考试不会考？
对，考试不会考得难。对，我觉得考试不会那么刁钻，我觉得。
没事，我应该是我数学所以可能比较失利，然后你就回去再好好复习。那你觉得如果像我这种小白的话，你会觉得要复习就是要然后是有时候会适应，然后又觉得复习要花很多时间，因为我看我实验室好像都是所有来学的，所以就只有我跟另外一个同学。对，还想说你会觉得这门课要复习，对于初学者来说会花很多时间？
我觉得不是太，但是我觉得从我角度来看不太准。对啊，但我觉得 回去看一次 slides 跟投影片，我觉得应该就够了。
然后再用自己的
对 slides 跟那个
去复习去消化。
对对对对，
好，OK，对。老师，那礼拜五的那个算是报告课
啊，
那老师会录影还是不会？就是
会录影，但是其实基本上大家不会看，因为其实那个大家就是分数是每个同学自己的分数，所以通常大家不会真的去看那个录影。
是，
对对对，
好，OK，对。可是这门课严格上来说，大概就是每周2个小时，再加1个小时的就是同学的报告。
对
，OK，好。
没错。